a couple of words about you. So,
okay.
Hi everybody. To have you all for synthesis of models and systems workshop. So we have the great pleasure to have a speaker today, Rajeev Alur, who's a Zinsman Family Professor of Computer Information Science at the University of Pennsylvania. So Rajiv's research is focused on formal methods for system design and spans cyber-physical systems, programming languages, and theoretical computer science. Rajeev is a fellow of AAAS, a fellow of ACM, a fellow of IEEE, and an Alfred P. Sloan Faculty Fellow and a Simons Investigator. He was awarded an inaugural CAV Award in 2008, the ACM IEEE Logic and Computer Science Test of Time Award in 2010, the inaugural Alonzo Church Award by ACM, SIGLOG, EATCS, Kurt Gödel Society in 2016, the Distinguished Alumnus Award from IIT Kanpur in 2017 for his work on time automata. So Rajeev served as the chair of ACM SIGBED, the general chair of LEAKS, and he was the lead PI of the NSF expeditions or he's probably still, I don't know whether the project is ended, the NSF expeditions in Computing Center ESCAPE, expeditions in computer augmented program engineering. And actually his talk is using part of the results of this project where he was a lead PI. And Rajeev is also an author of a textbook on the principle of cyber physical systems that appeared in MIT Press 2015. So as you can see, we have a really a heavy weight talking today. So a brace for an amazing talk. And I must say that I had the great pleasure and opportunity to work with Rajeev by the end of the previous century. And it was a great pleasure working with him. So Rajeev, the floor is yours. And thank you very much for giving the talk today.
Yeah, thank you, Radu, for that nice introduction. It's really a pleasure to be here. So thank you all the organizers to give me this opportunity to talk about work we have been doing on program synthesis. And as Radu said, so this work started as part of NSF Expeditions project, where the goal was to integrate many of the ideas that were around in program synthesis into some common infrastructure and some common computational core. And we call this problem syntax-guided synthesis. And so I'm going to give you a tutorial focused on that today. And it's supposed to be for 2 hours. So, but I hope it involves a lot of discussion. So feel free to interrupt me at any point in time and ask questions. You can also post your question in the chat window. And what I'm planning to do is to maybe talk for an hour, take like a few minutes break, and then we will continue. And at the end of the talk, we will leave aside some time to focus on future directions, and then maybe we can have more discussion. So I want to start this tutorial by first giving you a general overview of what synthesis is about and what syntax-guided synthesis is about, and focusing on the questions of why and what, right? So the background for synthesis is actually the success that formal verification has had in practice. So when I started working on formal verification, and this was actually in late 1980s, so at that point, verification, which it refers to checking that the program or a system satisfies a correctness property and trying to formalize that claim as a rigorous mathematical claim, and then building tools to verify that the model or the program actually satisfies this property. So this idea of formal verification, even though it started at the beginning of computer science in 1960s with a groundbreaking work of people like Tony Hoare and Dijkstra. So when I started working on this in the late 80s, it was still had not transitioned to industry. So it was always viewed as a desirable goal, but the technology wasn't ready. But over the last 20, 30 years, I think there has been enormous progress in verification. And a number of companies have now adopted verification as part of their technology. So it's not still like a technology that's commonly used by all software developers, but in niche pockets within industry, it's definitely used. And in particular, right now, a company such as Amazon in its AWS group, they have a very vibrant and thriving group of researchers focused on verification, and they're building tools so that they can give better assurance guarantees about the cloud infrastructure. So that's great. It's kind of a success of transfer of technology from academia to industry, but that raises this question that as academics, what should we be now focused on, right? And can we try to go beyond verification and testing? And the answer here is, one potential answer is to start looking at program synthesis. So program synthesis means different things to different people. The definition that I like the most is articulated in this wonderful article by David Harrell in an IEEE computer article in 2008. And the title of the article says, can programming be liberated, period. And that really is the vision that I think it's a good vision to have, that even though programming has evolved so much, from say 1960s to now, it's still focused on the programmer thinking about all the corner cases, filling in all the tedious details. And the level of abstraction has been raised through a lot of advances in programming abstractions and compiler technology and verification technology. But still, the programming, the way the programmer conveys the intent to the computer is still, in a very, using very rigid framework of some well-defined programming languages. Right? And in this article, he thinks about different ways potentially programmer could communicate the intent. And this is still a dream, but there are lots of technologies which are now can help us to move towards that. So there is a lot more computing power available. So questions that were viewed computationally infeasible a decade or two ago are now possible. The verification tools have matured. The HCI technology is evolving rapidly. The NLP technology is also evolving, and that's so that's a reason for hope. But that's a more long-term goal that programmers will actually convey their intent in very different ways. But the focus for this talk and the framework of syntax-guided synthesis was motivated by these 4 concrete applications. So one is programming by examples. The second one is about super optimizing compilers. The third one is kind of local edits to programs, what we call program repair. And the fourth is enabling as an enabling technology for verification itself. So synthesizing proof objects. And I will give you intuitive examples of these 4 applications in the next few minutes. So first, let's look at programming by examples. And here is my favorite example because it's very easy to explain. And it's from this very old book called Hacker's Delight. And this Hacker's Delight book contains lots of very clever low-level C programs. And here is one example. So suppose the transformation that you want to do is a transformation on bit vectors. And what we want to do is to reset the rightmost substring of contiguous ones to zeros. So writing this as a program can be a bit challenging. I mean, of course, you can write a loop which, where you start scanning the bits one by one, starting at the rightmost end, and then look for the contiguous sequence of ones. But you can actually specify this more intuitively and more easily just using a few input-output examples. So here, on this slide, I have shown 3. So for example, the third example says that if the input vector is 1, 0, 1, 1, 0, it should be transformed to 1, 0, then the 2 ones change to zeros. And right, even for even for experts, writing this program could be more challenging. But giving examples, I think it's we can all agree that it's easy. It's an easy thing to do for expressing intent for all kinds of programmers, expert programmers, beginning programmers, students, people who don't know that much about programming. Right? And what we want to synthesize is a program constructed from standard bit vector operations in C. Now, the C language actually offers a large variety of bit vector operations, and there are shifts and bitwise ands and so on. And it turns out the simplest program which can implement this. It's kind of cryptic, but where here X is viewed as a vector, and is bitwise and plus is bitwise OR, and so on. So the exact details of this program are not relevant for the talk, but this is something that the current synthesis technology can do, which is takes a few examples and take the space of programs through which it's searching and come up with this solution, right? Of course, if you haven't seen this, you would immediately start asking questions like, can we specify the program unambiguously using a few examples? And how can we provide support to the users so that they converge on the right program? And also, how do we actually search? Because even though this program seems small, there are lots of operators, and the search space is going to grow exponentially. So how do we manage that complexity, right? But these are exactly the kinds of questions that the synthesis research attempts to address. And this programming by examples, which actually can be, in fact, useful in an industrial context. And this is a nice success of this. And this is a project at Microsoft, started as a research project at Microsoft Research by Sumit Gulwani, and it's called FlashFill. And this is in the context of transformations in Excel spreadsheet, which is used by millions and millions of people. And if you have used Excel, you would know that Excel provides lots of built-in transformations to generate columns from the existing columns. By if you just wanted to add 2 numbers, you can just press on add, and then it will create a column which adds those 2 columns. But if I have a slightly more complicated task, and what you see here in my example is that the left column had some telephone numbers. These are the US telephone numbers. And the right-hand column shows these numbers in some cleaned up format, right? And if you think about the program that's actually doing this transformation, it's going to be some string transformation. But even with these examples, you can realize that, oh, this string transformation could be kind of complicated, right? And if it's not provided as a built-in functionality, for an end user to figure out this string transformation is going to be complicated. So even though Excel provides some built-in macro language to write string transformations, very few people will be able to write the desired program in this case. But to give examples is very easy in this case. You could just highlight a few rows and then show what output you want. And then what the synthesis tool is going to do is to search through the space of string transformation programs that can be written in Excel's macro language and find the one that best meets the user intent, as demonstrated by a few examples. And so this actually idea appeared in a Popple paper in 2011, and then Microsoft really liked it, and it was then integrated in Excel, and it's now shipped with Excel. And this is a quote from Wired, which says that, oh, why didn't PL folks figure out this type of feature already? This makes perfect sense, and this programming by examples is the right thing to do in this context. And here is my another example, actually more recent, and this is based on a project at University of Washington, where now what we want to do is synthesize SQL queries. And so on the right-hand side, you see a SQL query, and specifying it again requires some training. So of course, we teach all undergraduate students when they take database course, how to write queries in SQL, but it's highly specialized. And on the left, what you see is just one example where T1 and T2 are input tables, and out is the output table for this specific input tables. And the what the synthesis tool then does is uses these examples to generate this SQL queries. And this is implemented in this tool called Skype. So the second example I wanted to give about synthesis was to do with program optimization. So the programming by examples was aimed at end users, people with not much programming background. Can they express the logic? And in that context, it had to be very simple logic using input-output examples. At the other end, maybe programmers are experts, but they want to extract very high performance from their code. And so in the innermost loop, they want to do very efficient computations. Or maybe they want to port it to a new platform, and then the intricate details of that new platform are slightly different, and they want to see if how best to optimize the existing code on this new platform, right? And so this in compiler literature, this would be called super optimization. So I want to really optimize the code. If I have 10 instructions, from that I want to go to 8 instructions. So that type of transformations cannot be done by traditional compiler optimizations that you see, let's say, in a GNU compiler, because all those optimizations typically are structure preserving, they are local, they are semantics preserving code transformations, for example, removing an update to a variable from inside the loop to outside the loop if certain conditions are satisfied. But in the setting of this super optimization, the transformed code may look very different. And this actually is an active area of research. And I'm going to just show you a simple example to give you a flavor of what one could do. Though the example is pretty simple here. So here I want to take average of 2 numbers, x and y. So these are integers, and let's say they're 32-bit integers. And if we just set the average to be x plus y over 2, that actually is not quite correct, because that could cause an overflow. And so this is people who are building like core libraries, they would avoid this type of a mistake where taking average by adding 2 numbers is kind of a no-no, because that could cause an overflow, right? So how do you do this? Well, if you want to do it correctly, this is one way to do it. So you port x to a 64-bit vector x1. So so x is a 32-bit number and x1 is a 64-bit number. So then if you change x and y to 64-bit numbers, then you can add them, and you can be sure that there is no overflow, and then divide by 2, and then you know that the result has to be 32-bit numbers, so you can then drop off the higher order 32 bits, right? Yeah. So this actually turns out to be inefficient. So it's correct, but we can think of this as the specification and then ask ourselves, can I do without using 64-bit numbers? And this is something that even if you think about it, you would be hard-pressed to do it. And it turns out this is the answer here. Again, a cryptic-looking program which uses XOR and ANDs and shift rights, and it's semantically equivalent to the program that that's shown above, and does not use any 64-bit numbers and can be proved semantically equivalent, and is small enough that our current synthesis tools can synthesize. The third example I had mentioned was program repair, and this can be best illustrated in the context of giving feedback to programming homeworks by students, right? And this is an example derived from a paper by Rishabh Singh on a tool called AutoGrader, and this was published in PLDI 2013. So what you see here is a Python program that a student could have been asked to write in an introductory programming course. And here the goal was to compute the derivative of a polynomial. So the input polynomial is represented as a list of numbers, and those numbers encode the coefficients of the polynomial. And the programming assignment was to output the list of numbers that correspond to the coefficients of the output polynomial. And the output polynomial is supposed to be the derivative of the input polynomial, right? Again, the exact, we don't have to go through this code, but this is a solution that the student submitted. And typical tool for testing student solutions would just run this code on a few inputs and match them against outputs. And if it's not quite correct, they would say, oh, your output is not right on this specific input. And then the student would have to go figure out, what went wrong. And particularly when they're just learning to program, that could drive them to frustration, right? So what we want to do is to give very accurate feedback. And how can we give very accurate feedback? Well, if I can do a number of edits to this code and see which of the edited version actually is correct, then I can take the diff between the corrected version and the original version, and then give the student very precise feedback, right? And that's what this tool does. So what it needs is the student solution that's, there's something like this that's submitted, a reference solution, and some edit model, or what are the typical errors that the student is likely to make. Well, for example, someone may think the array indices start from 1 instead of 0. Well, then you could change ones to zeros and so on, right? Yeah. And then the synthesis task is to find a minimum number of edits to the program so that the student solution becomes equivalent to the reference solution. So how do you check this program equivalence? Well, it could be through some tests, or it could be using verification technology. So that's kind of orthogonal to the way you look for repairs. But the synthesis tool's task is to just try out these different edits. It's, of course, a large space, so there is still this issue of how do you search in an efficient way. And then, so the specific tool then would come up with the following feedback saying, your program requires exactly these 3 changes, right? And this is, so the only technology which can actually identify such correlated errors, which are very low level, is based on program synthesis. And my final example, and I'm going to show this quickly, is to actually generate invariants automatically. And so this is an example program with doubly nested loop for selection sorts. And what we want to prove is at the end that this array is sorted. It contains numbers in increasing order. So the key challenge in doing such a proof is coming up with this invariance. And if the user provides this invariance, loop invariance, then the verification technology is at a stage where they could actually check that it's a correct proof, right? But then the challenge is, how do you come up with this invariance? And the synthesis-based solution is that you ask the user to give some kind of a template for these invariants. So for example, the first invariant here says that, well, it involves these auxiliary variables K1 and K2 in addition to the program variables. And then it's a conjunction of 2 atomic conditions over all these variables. And you can then give this to the synthesis tools, and it can fill in those blanks and say that, oh, this is the invariant that you want, right? So so instead of specifying the exact invariance here, the person who is doing the verification has supplied some templates for these invariants, and then the synthesis tool has filled in that template. So things that you see in red, those are the tricky ones to figure out, and then it's guaranteed that this is actually an invariant, right? So I have shown you basically these 4 examples. We know it's programming by examples, program super optimization, program repair, and template guided invariant generation. And so when we started this work, we realized that there are the computational problem at the core of all these synthesis projects is finding a program that meets a syntactic constraint, right? And so in the case of template guided invariant generation, the template was the syntactic constraint for the invariance that we were looking for, and a semantic constraint. So for example, in the invariant generation problem, the semantic constraint would be that the synthesized invariant is indeed inductive, so it's preserved by the loop, for example. And so we want, so this is the core computational problem, and that motivated us to define this problem of syntax-guided program synthesis. So to contrast it with the classical program synthesis, which was actually formalized by Church in 1957, where in classical synthesis, you have a logical specification, what the program should be doing, and the synthesizer is supposed to generate the implementation. So the specification is, in the classical setting, it's a logical relation between the inputs X and outputs Y. So it's a formula in whatever logic that you pick, so phi of XY. And the synthesizer is trying to do a constructive proof of the following higher order formula. There exists a function f such that for all inputs X, the desired logical relationship between X and the output produced by f on X holds, right? And the constructive proof here so will give you the function f of X, right? And there has been decades of research in actually realizing this goal. And so, for example, Kestrel has a variety of tools where they, in fact, rooted in constructive mathematics, where you actually try to construct this function f. But this turns out to be a very hard problem. And for the kinds of problems that we looked at, programming by examples or some local repairs to the programs, this is, I think, a too heavy a solution. And so the syntax-guided approach then is to have an additional input to the synthesizer, which is the syntactic specification. And it's going to be a set of expressions, which we will see how it's formalized in a few minutes, but can be specified by context-free grammar. And then the key difference is that the synthesizer is now doing a search. Of course, one may argue that in any proof-based techniques, you are also doing a search, but here it's actually the search is more explicit. You are explicitly searching, and this could be using optimized search or could be using machine learning techniques. You are searching for an expression in this set E of expressions such that the expression satisfies the logical formula, and now checking that this synthesized expression size satisfies the logical formula can be done using existing verification tools, right? So we call this syntax-guided synthesis, SYGUS for short, and this website here, sygus.org, has a lot of information about this project. So I'm going to now tell you about formalization,
so Rajeev,
but it would be a good time to get, to have some questions. Yeah.
Yeah. So this is Radu. So if you go back to the previous slide, I was wondering this input-output. You have that example where you had these strings and you were zeroing the ones, the sequences of ones. So would this be a set of expressions? I mean, so would be considered, I mean, these examples?
Yeah, no, that's a good question. No, so that will be encoded in the logical formula. So the logic, so the semantic specification in that case will say that if x is equal to this, let's say 0, 1, 0, then x equal to 0, 1, 0 implies y equal to say 0, 0, 0. So, so the example.
Okay, and the set of expression would be the program, would be the and the or and this operation that you
Right.
are allowing.
The set of expressions would be all C programs that you can construct using the bitwise, the operations on bit vectors.
And how do you do the search? I assume that these are not, you cannot do kind of gradient or something like this. So you just do a complete search, or how do you search for the?
Yes, no. So yeah, we will get to that. Yeah.
All right.
So so I'm going to tell you about the current techniques that have been used in search.
Thank you. Thank you. So I see some other guys looking like Ras. Do you have some question? Maria.
Yes, thank you. I only have a comment about the history, the very early history. You had the page about Alonso Church initiating the first definition of synthesis. But I remember reading once that also at the very beginning of artificial intelligence, people thought that generating programs would be a sign of artificial intelligence of the computer. And back then they called it automatic programming rather than program synthesis. And I don't know whether it is really historically the same, but it was considered one of the goals of artificial intelligence to enable computers to generate their own programs.
That's a very good point. I think the original idea was by Church, but of course, automatic programming. I guess there was a lot of work on automatic programming in 60s and 70s, and then in the 80s there was a lot of work on inductive logic programming, and all of that can be viewed as program synthesis. So yeah, so this is not a complete history. So this is kind of just a starting point. And so within AI, within software engineering, so in many fields, program synthesis in different forms has been viewed as like a holy grail. And it's, but I think that's a good thing. So this seems like something that people desire, that the technology should be there. Yeah.
So I guess Ružica has a question for you, Rajeev.
No, I also just wanted to follow up on that I actually did ages ago read automatic programming paper, and I think it was even a different, I mean, it was just one of the sub goals that what the future should bring. And I recall that we tried to, it was actually about a simple sorting algorithm, if I recall properly. And funny enough was that we found that there was some error in the quantifiers. I think the quantifier was supposed to be at the wrong position. I did that with Berfing Weiner, our previous speaker. And what is interesting is at that time, they were already using existing tool that was called QA3, that was at SRI. And I think that they didn't manage to synthesize, although it was a very simple algorithm. And now the question was like, when Ben and I were asking ourselves, was it because of this error in the quantifiers, or was it indeed because at that time, even simple sorting algorithms were out of the reach of the tools? So just another comment. Thank you.
Yeah, thanks, Rajeev. Yeah, no, I think there is a rich history, but this actually is a good point for me to say one thing, is that if you look at more classical work on program synthesis, it was focused on things like sorting algorithm. Sorting was considered like as a test case. Can you synthesize like this different sorting algorithms, and the specification of a sorting algorithm is clear. I think in the current version of synthesis, we do not, I don't think that's the focus. I think we are looking at more practical uses, and the ones that I mentioned, like, can end user synthesize a SQL query from giving a few examples. I think that's maybe more modest, but it's also more relevant. I think it's not clear who wants to actually synthesize a sorting algorithm. So I think there is a shift in focus, and that has helped. Okay, but this was great discussion. So let me actually continue. So
before you go, Rajeev, there is one more question for Supratik. He raised his hand, so let's give him a chance. And then,
Hi, Rajeev. A quick question is that when you say the set of expressions which form the syntactic guidance, so we are including loopy programs with loops also as part of that, or?
It's a good question. I think it will become clear when we, let me actually
okay, sure.
Move to formalization. So what I talked about was more like motivation and giving you different examples where this syntax guided synthesis shows up. But let me now make the question more formal, particularly for this audience. I think this would be the right thing to do. So intuitively, it's, we have a set of programs. Actually, I think calling them programs is a bit misleading. These are more like expressions or program snippets, and that's the syntactic constraint. And then I have a logical specification, which is a semantic constraint, right? And what we want to do is formalize this on top of SMT infrastructure. So I think in this workshop series, there is also a workshop on SAT and SMT. So many of you must be familiar with it. But just for those who are not super familiar with SMT, here is like one slide summary. So SMT stands for Satisfiability Modulo Theories. And the core computational problem is given a logical formula, check if it's satisfiable. The formulas that we are looking for usually have not just Booleans, but bit vectors and integers and more complex types. And modulo theories refers to the fact that the interpretation for these additional symbols, for example, if I'm using integers, the formula may involve addition, multiplication, and so on. The interpretation for those symbols is fixed. Right? So we are looking for a satisfying model where the model satisfies some constraints of the underlying theory. So in the case of integers, it would be the linear. Say if you have linear arithmetic, then it would be the interpretation given by linear arithmetic to symbols such as addition. Right? So this has become a major breakthrough in computer science, designing efficient solvers to check formulas for these different SMT theories. And so we thought that we should build our framework, the standardization of this syntax-guided synthesis problem on top of that, right? So, so a number of technologies contribute to SMT. So satisfiability solver SAT is one, but linear arithmetic, there is a particularly nice construction for doing congruence closure. And a combination of these actually give you very efficient SMT solvers, right? So, so with that background, now I can actually define this Zygus problem formally. So you fix a background theory. So, it could be linear integer arithmetic. So that fixes what types of variables are allowed and what operations on these variables are allowed. Then you specify the function that's to be synthesized. So, you may say, okay, I want f of the type int cross int to int. So in general, there could be multiple functions, but for the purpose of this talk, let's assume we have only one. And then the input to the Zygus problem consists of two things. So one is the specification, that's the logical constraint or semantic constraint. And it's a formula that involves symbols in this underlying theory and the symbol f. That's the one that you are trying to synthesize, right? So if you know about SMT, then this f is not an uninterpreted symbol. It's really the function that you want to synthesize, right? And of course, there could be uninterpreted symbols because the underlying theory could be, the theory with uninterpreted functions. And then the set of expressions. So that's the candidate. That's the space of candidate implementations that you are going to search through, and that's given by context-free grammar. So we are assuming that context-free grammars people are very familiar with. Anyone working in this space will be familiar with SMT, and that's the extra technical stuff that you need to know to generate these Saigas problems. That's relatively limited. Right? And then the computational problem is now precise. So you want to find an expression small e in this set capital E specified by the context-free grammar, such that if you take the SMT formula, which is given as a logical spec, and substitute this expression E for the symbol F, then what you get is valid. Right? So it's, it should hold for all inputs. And this appeared in a paper in FMCAD 2013 as part of this ESCAPE project with a number of people, including Ras Borik, who is here, and Sanjit Seshia, and Armando Solar-Lezama, and a number of students. So just to give you an example, so suppose I fix the theory to be QFLIA. So this is kind of SMT lingo, but basically it means quantifier-free formulas in linear integer arithmetic, where the types are integers and booleans, and you have logical connectives, conditionals, and then you say that, okay, the function that's to be synthesized is f, which takes two inputs, x1 and x2 of type int, and returns int. And the specification says that x1 is less than or equal to the output of f, and x2 is less than or equal to output of f. That is, f should compute a value which is greater than or equal to both its inputs. So this does not fix the f uniquely, but that's the computational problem. Find f, and presumably the simplest f with with this which satisfies this specification. But the nice thing about Saigas is that you can also specify the grammar separately, right? So suppose I want to see if a linear expression, can f be constructed as a linear expression? Then I can specify the following grammar, which is the desired f is either the inputs or a constant or sum or difference of expressions, right? So this is a precise specification of this syntactic space. And if you think about it, that if I want f to be such that it's greater than or equal to both its inputs, and the only constructs that I have is are just addition and subtraction, then in fact no such f exists. I mean, no matter what linear combination of x1 and x2 you construct, you can't guarantee that it's always will be greater than or equal to both x1 and x2. So then I can go and say that, okay, can I find something with conditionals, right? Yeah, with if then else, where but now I want to see if the expressions without addition, can I find an implementation that uses conditionals but not addition? And in this specific case, it turns out indeed there is such a solution, which basically says if x1 is less than or equal to x2, then x2 else x1. So this is really max of x1 and x2. If you think about the specification, so it's not specifying a function uniquely, but max of x1 and x2 definitely satisfies the spec. To compute max, you need conditional, you don't need addition. And by varying the syntactic space, you can control the search space, and you can also control what type of solution that you want, right? And the current Saiga solvers then can, generate this. So this is how the, the syntax looks like. So in SMT, the standardized format is called SMT lib. And the format that we have is called synthlib. It looks very much like SMTlib with some extensions. So the set logic li says that, okay, the underlying logic is linear integer arithmetic. This synthfun is a new keyword, which is special to the synthesis part. And it says that it declares max2 to be, it declares its type, and then it has the grammar. And then you have the constraints are the constraints on the desired max2. And this checksynth command then says that synthesize a function max2, which satisfies these constraints, right? Yeah. So of course, yeah, we don't need to focus on the details of the syntax. I wanted to show you this to just suggest that it blends with SMTlib nicely. And now actually Andrew Reynolds, who maintains SMTlib very actively, he has gotten involved in Cygus and Synthlib, and he has made sure that the current versions of SMTlib and the Cygus formats are all in compliance. They all match. So I had mentioned 4 different problems. So in interest of time, I'm just going to focus on one of them, how to formalize it exactly as a Cygus problem. So suppose I want to find inductive loop invariance automatically. And here is kind of a sketch of some potential program. Has say 6 variables, x, y, z, that are Boolean, a, b, c are integers, and there is some test. So it has a single loop and some loop body, and there is some precondition and a postcondition. And the goal is to find an inductive invariant so that the proof goes through, right? And I want to set up the question of generating the invariance as a Cygus problem. So first we have to declare the function to be synthesized. So let's call it inv. And this is, suppose I want to say that the desired invariant involves only x, z, a, b. Then I can declare this as a type, saying that, okay, it takes x, z, a, b, and returns a bool. Invariant is a, it's a Boolean, it's a predicate, so its output type is bool, and it takes only 4 things. So it's like giving a hint to the synthesizer that the desired invariant, instead of involving all the 6 program variables, involves only these 4, right? Then to generate a logical constraint, we need to compile the loop body into a logical formula. And assuming this loop body itself doesn't have internal loops, we can compile it into a formula. So this is a standard verification technology now, so like generating verification conditions. So this update is going to be a formula that involves the old program variables and fresh copies, which will reflect the updated values of all these variables. So it's a formula between old variables and updated variables. And now the specification of the desired function inv can be that the precondition implies inv. If inv is satisfied and test fails, then the postcondition should be satisfied. And if inv is satisfied, and if we update the variables according to the formula update, and the updated variable satisfy test, so the test primes refers to that, then the updated variable should satisfy the invariant. So that's like saying that the invariant is inductive through one execution of the loop, right? And then we can we want to synthesize such an inv, and the syntax guidance can be provided by defining the template for what kind of inv that we want, right? And so, for example, if I want to say that it should involve conditionals and linear arithmetic, then I specify the grammar for inv, right? I could specify, for example, that inv involves only 4 conjuncts. Well, I can specify something like that. So this is how you can go from template-guided invariant generation to this. And a number of benchmarks from the software verification competition that's usually held with ETAPS have been translated to get a whole bunch of benchmarks for Cygus. And then the benefit is that now you can actually focus on the core computational problem of how to search through the space of all potential invariants without worrying about a lot of front-end details. And if we were looking at programming by examples, then the template would actually specify the grammar of the expressions that you're looking for. And then the specification there would be much easier. It would just say that on the given, if I had 5 input-output examples, it would just say that and over all those 5 examples, on that specific input, the output should be the desired one. But usually, we can also augment the specification by adding some integrity constraints. If we know that if there are some logical constraints that the all programs should satisfy, then you could add that to the specification. So some domain-specific knowledge could be built into the specification, and that's what we will typically do in PBE. And in the second half of this talk, actually, I want to give you a specific application related to synthesizing network traffic classifiers, and we'll get back to this at that point. So that was like the formal definition of SIGAS, and in the next part, I want to talk about some solution strategies for SIGAS. But this again would be a good time to take some questions.
So any questions? Because this is a good time, because then actually after the questions, I think we could take a short break, let's say 5 to 10 minutes. Get it, and then other questions. If questions, please raise your hand. Yes, Maria, do you have a question? I'm seeing you working.
Yes,
so
thank you.
you.
Could you please just go back to the slide, to the page where you introduced the paradigm for syntax-guided, exactly, this one, exactly, the complete, exactly. So fixed background theory, function to be synthesized, general case multiple function, and then we have specification, type formula, the set E, and computational problem. Okay. But then, thank you very much. But then all the other problems you enumerated later, namely find inductive loop invariant automatically, function to be synthesized, compile loop body, etc., etc. I'm sorry, but I didn't see all the connections. So are they all instances of the general syntax-guided synthesis problem, or they are subcomponents of the syntax-guided synthesis problem?
The former. So so for example here, let me go back to this inductive invariant thing, right? So so given a program, I want to synthesize invariant, and what's saying that this question can be formalized exactly as a SIGAS problem. So what's the underlying theory? Well, depends on what kinds of invariants you're looking for. So you say that, okay, I want my invariant to be, say, a linear expression. So you would pick LIA to be the theory. The unknown function is inv. And so instead of having all program variables involved in inv, I could change its input type to restrict the search space, which is more like a hint. Could say that, okay, the invariant in this case, instead of all these 6 variables, involves only 4. The output type of desired inv is bool. Then this compilation step is automatic. And then this is the logical formula, which says that, pre implies in and not test implies post, and in and update and test prime implies in prime. So this is really specification of what it means for inv to be an inductive invariant that's strong enough to prove the correctness of the program. And the syntactic guidance comes from which template do you pick, right? So the that's that's what's going to be. So this question then can be translated to something like this. And so we have a whole bunch of benchmarks where questions about automatic generation of invariants for C programs from this software verification competition, they all get compiled into something that looks like this. And the unknown function there, so here in this example was max2, there it would be the invariant for that specific program. And these constraints would then capture the, I guess, the update functions for those specific programs. So I didn't go through the other examples, yeah, but programming by example or program repair and so on, they all can be formulated exactly in this framework. So there is work on so maybe so I think this yeah, let me just show you one thing before we take a break. Yeah, so I think it's going to look like this. So this is the intermediate format, and then the invariant generation. So there would be a front end which takes your program and then compiles the problem of generating the desired invariant into something that looks in our format. And then the programming by examples also could be compiled into instances of this syntlib. And so then the people who are working on these backends could just focus on how best to optimize the search. And this SYGUS could be used for some other applications besides these 4 that I have shown.
So does this answer your question, Maria?
Oh, yes, thank you very much. Great, thank you.
So Supratik has also a question. You want to go ahead?
Yeah, hi Rajeev. So can you go to the slide on invariant generation? Yeah.
Yeah.
Yeah, thank you. So how is this different from constrained horn clause solving? I mean, this looks very similar, right? I mean, is it just in the syntactic template that?
Yes, yeah, definitely. Yeah, I mean, it's a specific formalization of it, and then using horn clauses would be a different formalization. Here, the key is really the syntactic template, and you can vary it. And you could, I think, in many other approaches, maybe the syntactic template is implicit. Here, it's an explicit input, and you can change it.
Okay.
And but the syntactic template is an input to the to the synthesis routine. That's key, right? So it's generic. It's in some sense the way synthesis works is it's not tuned to a specific template. It takes the template as an input.
Pardon me, it's not due to a specific what?
No, it's the template is an input to the SYGUS problem.
Yeah, yeah.
So yeah, so it's just another input, right? So this synthesis problem has 2 inputs: the logical specification and then the template specified using context-free grammar. And you want a synthesis tool to work for no matter what the input grammar is and what the input specification is.
Okay, thank you.
All right, so let's take one more question, and before we go to the break. So Mark has a question. They want to.
Yeah, so I was just wondering, we have the invariant generation, we can also synthesize program expressions. Do we have a way of synthesizing both the loops themselves and the loop bodies at the same time? Is that something we can cite?
That's a good question. Well, in theory, you can. I mean, you can formalize it. The question is, will it work, right? Yeah. So our current benchmarks don't involve such more ambitious thing. Yeah. All
right, then I think we should take a 10 minutes break. So it's now 6:30 in Vienna. So anyway, it's past 1/2. So let's meet at 40 past. Is that fine with you, Rajeev, or should we?
Yeah, thanks. Yeah.
All right. So let's take a 10 minutes break for coffee. All right. See you later, guys. So I guess we can talk later, Rajeev, about this, but I think it's interesting. What is the nesting depth that you can get in these expressions?
Oh, the one that we can actually synthesize with the existing solvers.
Yeah, yeah.
So the I guess it could be about 100 ASP nodes.
Uh-huh.
So the
depth,
I don't know, but because in the end you are synthesizing an expression, and the expression is specific. It's represented by its abstract syntax tree.
Mm-hmm, mm-hmm.
So yeah, I guess 100 nodes.
So it's hierarchic in some sense. So you can explain what you have synthesized pretty well.
Yeah, interpretable. Actually, yeah. So I think I have some examples for this network traffic classification, and
yeah.
So I should. Yeah, I'm going to skip some parts of the tutorial so that we get through.
Yeah. All right. So we are going to start like in 1 minute now. But that's a huge advantage. I mean, compared to let's say deep neural networks where they have no idea what to synthesize. I mean, that's
So in fact, I think this network traffic classification. I want to get to that point because that's an area where people were using machine learning, but that's a big problem. Interpretability. So this could be a solution. Yeah.
All right, so welcome everybody back. So let's continue with the second part. So Rajeev, your floor is yours.
Okay. Thank you, Raju. So I told you about how to formalize the problem, and now let me give you a brief idea about how do we actually solve this problem, right? So this actually relates a bit to the question that Supratik asked, that is Cygus same as solving SMT formulas with quantifier alternation, right? And the answer is not always. So if the set of expressions is, say, only linear expressions, right? So if I have two input variables, X and Y, then any linear expression over these input variables will be of the form AX plus BY plus C. So then we can capture the set of in an arbitrary expression with just 3 parameters, A, B, C, and then I can reduce the desired search to solving the quantified formula exists ABC for all X, some spec holes, right? But if I don't know the depth of the tree, right, the search tree, and not always an arbitrary tree can be captured by a small set of parameters, then you can't really reduce Cygus to this quantified SMT formulas, right? And but there is another reason to focus on this problem, because the syntactic structure that that we have in the set of candidate implementations that can be used effectively by the solver. And surprisingly, in fact, now the latest solvers for quantified SMT, and we did not expect this when we started this project, in fact, use Cygus. So if you think of a formula such as for all X, there exists a Y something something. So finding this Y is actually some function of X, and what we would call as the Skolem function in logic. So I can actually use syntactic guidance to limit the space of Skolem functions over which you are searching for. So the new approaches to solving quantified SMT, in fact, formalize it as a Cygus problem. So that's an interesting direction. But let me tell you about how do we actually solve Cygus. And so you can think of Cygus as an active learning problem. So there is a search algorithm which is looking for candidate expressions, and the verification oracle checks if the candidate expression synthesized by the search algorithm meets the specification. And if it does, then it can stop. If it doesn't, it produces a counterexample. And the way this works is that the search algorithm starts with some initial examples or initial outputs, initial input, sorry, and when the verification oracle says that the candidate expression doesn't satisfy the spec, it generates a counterexample which is added to the set I. And this can be best be understood with a little example. And this technique is called counterexample guided inductive synthesis, CGIS for short, originally proposed by Armando Solar Lezama, and has kind of become the standard technique for most of the SYGIS solvers. And here is the specification that we looked at earlier, that f should be greater than or equal to both its inputs, right? And for this part, let's assume that the set E of expressions is built from the input variables x1, x2, constants 0, 1, and say comparison and if then else, right? And initially the set I, which is the set of interesting inputs, it's initialized to the empty set. And the goal of the search algorithm is to find a candidate implementation for f from this space of expressions, such that f works at least for the inputs in I. Well, initially I is empty, so in fact any f would work for an empty set of inputs, and so it may generate x1, like a simplest expression, an expression of size 1, and so let's assume that it returns x1. So what it's saying is that x1 is a potential implementation for the desired function f, and this works for the inputs in I. And the job of the verification oracle is to plug in x1 for f in the specification and see does it work for all x1 and x2. And this check fails, and it returns a counterexample and says that, oh, if you set f to x1, for the input x1 is 0 and x2 equal to 1, the spec won't be satisfied. Because in this case, the f would return 0, and it's not greater than or equal to x2, which is 1 in this case. And now the search algorithm tries to find an f which works for this one specific input, 0, 1. And in this, so it tries to find the simplest implementation of f which works for all inputs in the set I, which currently just holds exactly one input, and it may return x2 as a candidate implementation. And the verification checks again the same thing. It says setting f to x2, will it work for will the specification hold for all x1, x2? And the answer is no. In particular, it wouldn't work for x1 is 1 and x2 is 0. And this process then continues. Maybe after another iteration, the set I contains 4 examples, 0, 1, 1, 0, 0, 0, 1, 1. And for these 4 inputs, so now the search algorithm is restricting its attention to these 4 inputs and trying to find an f which works for these 4 inputs. And then it actually has to generalize. And the implementation that it comes up with is if x1 is less than or equal to x2, then x2 else x1. And then the verifier checks that setting f to this expression, does it work for all x1, x2? And in fact, in this case, it will conclude that we have generalized enough, and the process will stop. So why is this good? So what's the benefit of CGIS? So actually, let me show it to you as an algorithm, and then it will become clear. So our goal is to find an f in a set capital E such that for all x in the domain of inputs, the spec holds. So there are 2 exponential searches here, finding f and then checking that for all x something holds. And so for the sake of argument, let's assume both of these are exponentially large search spaces. So the thing is, even though we have made so much progress in SAT, searching through an exponential space is hard. The cases where it works is when, when you find a solution, you can terminate early. So this for all x quantifier is kind of challenging. If I said that find an x for which something holds, that's satisfiability. So even though the space is exponential, SAT and SMT solvers work quite well when you can terminate early. And this architecture of CGIS has basically helped us set up two collaborating exponential searches. All of them can terminate early. So we set I to the empty set, and what we are trying to do in learning phase is find an F which works for all x in I. But now it's not really a universal quantifier, it's just a conjunction because the set I is finite, it's actually small. So the interesting search here is only finding an F, and the moment we find an F which works for all the current interesting inputs, this search can stop. And then the verification phase is actually trying to show that the F that the learner has learned doesn't work for some input. So it's really looking for an X for which these using the current F, the spec does not hold. And this this can be given to a satisfiability solver or an SMT solver, and that works fast. So the only time you are forced to search through all X's is upon termination, right? When you have found the right F, and then it would have to look for all, it would have to search through all X's, right? So, so in some sense, the universal quantifier gets applied only once, even though this is an iterative process, right? If you look at the original question, is there an F such that for all X? Well, for every F, if you try to apply that for all X search, then that's going to be very expensive. And that's why this CGIS seems to work quite well in practice. So there are three search strategies. So when we started this work, one was for learning. So for verification, we are just going to use an off-the-shelf SMT solver. But for learning or for searching, we need new strategies. And there were three strategies: enumerative, symbolic, and stochastic. In interest of time, I'm just going to show you the first one, enumerative, and just give you a flavor of what it does. And this was first in a paper we had in PLDI in 2013. So what's the specification for the enumerative search? So I have some finite set of inputs. I have a grammar that's generating a set of candidate implementations, and I have a specification. And I'm searching for an expression which works at least for the inputs in this finite set I. And the first attempt is let's just start enumerating these expressions in this set capital E in increasing size till you find something that satisfies the spec for all inputs in I. So of course this is too prohibitive, but remember that since the set I is small, if you look at a specific expression, checking whether it satisfies the spec for all inputs in I can be done very fast. Right? So what we want to do is actually prune this search and try to find techniques so that we don't have to look at all expressions. And then an improvement of this attempt, and actually this works quite well, and later we will see some more optimizations of this, is on this idea of equivalence of expressions. So let's declare two expressions, E1 and E2, to be equivalent if they give the same answer on all x's in the current set capital I of interesting inputs. And so initially I is empty, and as these iterations go, I will have a few inputs. So in general, actually this lots and lots of expressions will be considered equivalent because we are looking only at x's in this small set, right? And the key idea in pruning is that when a lot of expressions are equivalent, let's just use one of them for our search. It's some canonical representative. And not only discard these other equivalent expressions, but when we build more complex expressions, when we need a sub-expression, we are just going to focus on these representative expressions. And let me illustrate this with an example. So let's suppose my spec is f is greater than both its input. So I've modified it from the previous example for illustrating this specific pruning. And let's suppose my grammar says that it's either one of the inputs or the constants 0, 1 or the sum of expressions. And let's assume for now that I just consists of a single point, 0, 1. then we are looking for an expression generated by this grammar, which works for the specific input. So how would the enumerative search go? Well, it will first enumerate all 4 expressions of size 1. In this case, it's x1, x2, 0, and 1. So the key idea in pruning is to check, are any of these expressions equivalent with respect to this specific input, x1 is 0 and x2 equal to 1. And you would realize that, oh, in this case, 0 is equivalent to x1 and 1 is equivalent to x2, but the expressions x1 and x2 are distinct. Even on the specific input, they're distinguishable, right? So instead of having 4 expressions of size 1, now I have only 2 expressions of size 1. And furthermore, this actually bootstraps. Now I want to generate expressions of larger size. So, for this grammar, there could be, so the relevant rule will be E plus E. E can expand into, well, there are 4 expressions of size 1, but now there are only 2 that are inequivalent. And I'm going to focus only on these representatives. And the second E here will also expand into either x1 and x2. So instead of getting 16 possible expressions of size 3, I get only 4 expressions of size 3. And again, I check, are any of these equivalent to the ones that we already have on the specific input 0, 1, and we are going to discard these. And so the only one that will be left is x2 plus x2. So now I have only 3 expressions of size 3. And then as we go along, we are going to check if any of them satisfies the specification and stop the moment one of them works. Right? And so this simple idea, well, one has to do some algorithm engineering to implement it efficiently, but this actually gives us a lot of savings. And this is the basic idea in enumerative search. So in the interest of time, I'm going to skip over symbolic search, and there is also stochastic search. And but I will post these slides if anyone is interested in. But just to give you a flavor of how the search works. So with that, so in this original paper in FMCAT 2013, we implemented these 3 search strategies and evaluated them on some set of benchmarks. Actually, at that time, the conventional wisdom was that the symbolic search would do best. And but in fact, this experiment showed that the enumerative search, in fact, does better. And the motivation for setting up the standardized format and the competition was actually the success story of SMT, where once the SMT lib format was standardized and a variety of problems were collected and benchmarks were collected and an annual competition was set up, tools like CVC4 and Z3 kept on improving the backend technology, and a number of tools for verification, for testing of used this interchange format to focus more on the front end. So actually, so if you want to verify, let's say, C programs, a lot of action is really at the front end, and the constraint solving at back end is of course important. But if I can use it as a black box technology, then the work in a tool like CBMC, which is a bounded model checking tool for C, would be much more facilitated. So based on that SMT success story, we said, let's set up a SIGUS competition, and it's been held for 4 or 5 years now. And the driving applications were like program optimization and program repair that we talked about, and we implemented a number of these search techniques. So how have things evolved? So I'm just going to give you a flavor. So currently we have about 2,000 benchmarks collected from different applications. There are some special tracks, so programming by examples. So the spec is of a particular format, so some tools exploit that. When the grammar is conditional linear arithmetic, one can try to exploit the properties of linear arithmetic, and so that's why that's also a special track. And over the years, some new solution strategies and applications have shown up. So let me just illustrate one new solution strategy, just as an illustrative thing. and it fits well with the enumerative search that I talked about. So let's go back to this specification of max2 that we had, that the output of f should be greater than or equal to both the inputs x1 and x2. And the solution was, if x1 is less than or equal to x2, then x2 else x1. Well, this is not a complex expression, and we can easily, the current synthesis tools can easily generate this. But even in this case, observe that the size of the expression is much larger than the sub-expressions x2 and x1, which are of size 1. So actually, if you think of x2 and x1 as partial solutions, they cover the space of all inputs. And so this suggests a different approach to enumerative search by applying a divide and conquer techniques. And there is a very nice analogy, and not just an analogy, it's based on decision tree learning, and we will see that connection in a minute, right? So but at the high level, the core idea is that generate partial solutions that are correct on subsets of inputs, and then combine them using conditionals, right? So for this purpose, you will have to enumerate terms and tests for conditionals separately, right? But to see the connection to decision tree learning, let's go back to the enumeration strategy, right? So we were enumerating expressions like x1, x2, x2 plus x2, and so on, with pruning, right? So the pruning allowed us not to consider all expressions of size 1, but only representative ones on the given set of inputs, right? But suppose the current inputs, so suppose I had inputs like 0, 1, and 1, 0, so I'll have a few inputs. So you can think of inputs as data points and expressions as labels. And this edges says that, oh, the expression x1 satisfies the specification for the input 1, 0, right? So this I can think of x1 as labeling the data point, right? So the data points are these interesting inputs generated by the CGIS loop, and the expressions are the ones that are labels enumerated by the enumerative search. And so previous algorithm searched for an expression that was correct for all inputs. But now we could stop when we have enough coverage. That is, every input is correct for at least one of the expressions, right? And we can now enumerate predicates separately, and you can think of these as attributes, right? So you can think of the decision tree that you want to learn will have the data point, the labels at the leaves and the attributes at the internal nodes, because these would be our predicates, right? And the precise definition is that an input has an attribute p if the p of x holds. So for example, the input 0, 1 is the expressions x2 and x2 plus 2 are both correct for this input, and this data point satisfies the attribute x1 less than or equal to x2. So now we can enumerate expressions till we get coverage of all the inputs. Then we enumerate predicates, and then we apply a standard decision tree learning algorithm to compute an expression whose internal nodes will be labeled with attributes, and the leaves will be labeled with labels, which would be the expressions, and then that will give us the desired expression. And this gives actually a significant speed up. There's another technique where you can try to learn probabilistic models, but in the interest of time, let me skip that. Right? So just to give you a flavor of what kinds of things we can handle. So this slide is slightly old. So this is actually from 2017 competition, where we had about 1,500 benchmarks. So at that point, so depending on the space, so for the string manipulation programs, the resulting expressions had about 20 AST nodes, whereas for bit vector manipulation programs, we could synthesize expressions with 1,000 AST nodes. So this is a computationally hard problem. So depending on the class of benchmarks or even the specific benchmarks, the computation time could vary a lot. We had a number of participating solvers that year, and this euphony thing, which actually I didn't talk about, which combined decision trees with learned probabilistic models, was the best solver, right? And the typical time to synthesize, things, expressions of this size was about few minutes. The current winner is actually CVC4, developed by Andrew Reynolds and his team. So basically, CVC4 is a very robust and standard SMT solver. And what they did was a number of these enumerative search strategies, in particular this pruning based on expression equivalence, was integrated inside CVC4 itself. So we were treating the verification oracle as a black box, but there is obviously no need for that. The two could be tightly integrated. And so in 2019, CVC4 was the winner. And in fact, it was its performance was so much better than other solvers that in 2020, we did not find entries which were even competitive. So the competition was not held. So to have kind of the next evolution or next step, we need something better, that beats the current CVC4. A number of new interesting applications have come up. I'm just going to tell you a little bit about the synthesis of crypto circuits because it's quite cool. And this application came around after we developed the Cygus solver, so we are particularly proud of that. And it was done in Chao Wang, who is at USC in his group, and it appeared in this paper in CAV 2016. So, and it was kind of unexpected, sort of fixing circuits against timing attacks. So here is a cryptographic circuit where you have some inputs and then you have some outputs, and this is a real circuit. It's from this advanced encryption system, AES SBox implementation, first published in 2002. And so the goal of this circuit is that some of the inputs are public and some are private. And the goal is that if we change the public inputs, which may be encoding, say, a public key, and if you observe the outputs, you won't be able to infer anything about private inputs. And this circuit does satisfy that property logically. But there is a side channel attack. If I change a public input bit, and if I can measure how long it takes for some output to change, and if I do these experiments repeatedly, I will be able to infer something about the private inputs based on timing characteristics. And the high-level idea here is that if you, for example, if you look at this out AND gate, then there is one input which feeds immediately to the AND, whereas some other input feeds through a long chain of AND gates. And if the AND gates output changes from, say, 1 to 0, you'll be able to infer something about these two different classes of inputs, right? So that's the basic idea in the side channel attack. And this vulnerability was reported in 2014 in this paper in Date, and they said, okay, let's build a resilient circuit. And the basic idea, if you look at the structure of this fix here, is to make that all paths to have exactly the same delays by adding these dummy buffers, right? And this resulting circuit is functionally equivalent to the original one and has this property that it's constant time. The length, the path lengths from every input to every output is exactly the same. So, Chao Wang's group had this clever idea that they said, okay, let's set this up as a synthesis problem to finding an attack resilient circuit. And in fact, as a Cygus problem. So what's the precise specification? So given a circuit C, you want to automatically synthesize a circuit C prime such that C prime is functionally equivalent to C. So that's a semantic constraint, and in fact can be written in SAT. You don't even need SMT. And all input to output paths in C prime have same length. And this is a syntactic constraint, right? So if you think about the parse tree of the circuit, without knowing what the actual elements are, if I said that all paths are of same length, well, of course, you need some bound on the path length, but that bound is the max path length in C itself. So you write this grammar saying, okay, these non-terminals are generating circuits with path length 1, these non-terminals are generating circuits with path length 2, and so on, right? And you go up to path length, say 5, for example, in this case. And the one thing to note here is that even though there has been a lot of progress in EDA tools, you can't really set this up as a synthesis question because they are typically tailored to optimizing, say, timing or optimizing area or something like that. And usually they spend a lot of effort in developing optimizing for some specific measure. But now it's like a generic syntactic constraint, and you can just give it to Cygus solver, and surprisingly, it actually gives you a very non-intuitive and very compact circuit, which is shown here. So it's guaranteed to be functionally equivalent to the original circuit, and it's constant time, so it's at least resilient to this specific kind of timing attack. And if you compare it to the handcrafted attack resilient circuit reported in this paper, you can see that it has much better quality because it has fewer gates and fewer path lengths, and it's also generated automatically. So this is an example where the infrastructure we built actually helped. And but let me actually spend next 10 minutes, and then we will go to discussion about future directions, about some application we did very recently. And I think this is there is a lot of potential here. So I want to tell you about this. And it's kind of a bittersweet because we couldn't use the existing Cygus infrastructure, though a lot of ideas were useful. And this is reported in a paper in upcoming TACAs, and it's for network traffic classification. So what's the application here? So, in the network switch, you have a stream of packets, and the switch is deciding whether to drop the packet or whether to alert a controller and so on, right? And so this network traffic engineering is a big field where people want to detect attacks. So an example attack could be what's called DDoS. So it's a denial of service attack, and it's a flood attack, which basically says that some IP addresses in certain range are opening lots of connections, could be TCP connections, within a short time window so as to exhaust the resources at the server. So, this has a clear pattern, right? You want to count how many connections are open. Are they from kind of similar IP addresses? They have to be within a short time interval, but you also need to know, what's the, what's an open session. So it requires some kind of pattern matching over the input traffic, right? Yeah. So, so this actually is a great opportunity for synthesis. That if I gave you positive and negative examples, so if I said, oh, here is kind of a new problem. So today's attack, the server is exhausted, so it must be some new attack, which I don't know about. And so today's traffic looks quite different from, the traffic of the past days. So think of the past days as the traffic from the past days as positive examples, and the traffic from today as a negative example, and find me a classifier, right? So compared to, the first example I had used was FlashFill, where the inputs were like these strings, like, phone numbers and names and so on. Compared to that, here, your input example here is actually raw network traffic, which is thousands and thousands of packets. So a kind of a very different beast here. Particularly for the anomalous traffic, you have very few examples. For positive traffic, actually, you have lots of examples. You want high accuracy because if you say that, oh, the operator will have to examine what you have generated. If you are giving some false reports, they would be quite annoyed. So people have tried to use machine learning, but one way where program synthesis can have a win is that the output classifier, if it's interpretable, if it's in some domain-specific language, that would be great, right? Because then the operators can understand it, they can edit it, and so on. A key requirement here is that what you synthesize has to be implementable efficiently on the router, because the whole point of having having a classifier is to actually run it dynamically on the router and reject the traffic which matches the anomalous pattern in the future, right? And we want this to be expressive, so that there are this traffic has lots of rich features. There could be session layers, application layers, and the attacks could be at any level, and all of them should be expressible, right? This is a very active area. If you are interested in what machine learning based approaches look like, state of the approach for this problem, I would recommend this paper from NSDI 2018. It's a system called Kitsune, which is uses autoencoders, and they have lots of these advantages, except that it's not interpretable. And what we are doing is hopefully better, right? Yeah. So what can the program synthesis-based solution look like, right? So the first step is choose a suitable DSL for traffic classifiers, right? So, in the case of say linear integer arithmetic generation of template-based invariant generation, we know what the DSL looks like. It's some combination of these linear expressions. Here, this is actually a new space, right? In fact, even for FlashFill, a lot of effort and ingenuity was in designing the DSL that the FlashFill goes through. For synthesizing SQL queries, it was SQL queries, but this is kind of different, so we had to work on that. So it should be expressive enough to capture a variety of attacks. It should have built-in abstractions for succinct descriptions. And then the second step is design a synthesis tool, which actually finds a succinct expression in this DSL, and it should be scalable to generate interesting classifiers, right? And the new challenge here compared to state-of-the-art synthesis technologies, this ability to handle traffic, which is like thousands and thousands of packets, right? Yeah. So the tool that we built is called SharEngine, and the DSL that we use is actually, it's called NetQuery. I'm going to skip through these few slides because I think this is kind of orthogonal. But we had designed actually a nice DSL called NetQuery, and this was in a SIGCOMM paper a couple of years ago. And you can, the basic features of this are actually here. So it's built on top of regular expressions, but something we call quantitative regular expressions, where regular expressions are merged with aggregate operators like max, min, sum, average, standard deviation, and so on, like an expressive set of aggregates. A lot of domain-specific features, so like ports, IP addresses, ranges of addresses. Then you can do a group by on IP address keys. So things very specific to network traffic, references to time windows. And in this setting, the expression maps an input traffic to a numerical value, right? So for example, in that DDoS attack, we wanted to count the number of open TCP sessions, right? So the expression should map, a network trace to some numerical value, right? And so in the SIGCOMM paper, we had actually defined this language NetQuery for a different purpose, to actually thinking about high-level programming abstractions for network traffic engineering. And now actually we can use it for the synthesis purpose. But as part of that effort, we had actually developed an efficient compiler and runtime system, which takes a NetQuery expression and actually can run it on a switch, right? And the kinds of things that you can actually express in this language are, flow-level traffic measurements. So there are these concepts like heavy hitters and super spreaders in network traffic engineering. So those could be expressed. You can detect synth-flare attacks, aggregate statistics over TCP connections. And compared to C++ code, this could be quite succinct. So we had like a complex application level monitoring property about voice over IP sessions, which could be expressed with a NetQuery expression with 18 AST nodes. So well within the scope of synthesis tools. And if you were to compile it into C++, it was like about 500 lines of code, right? So clearly we should be searching through DSL. And of course, if you don't like NetQuery, we could use another DSL, but it should satisfy this, should be expressive and should allow succinct expressions. So this DDoS attack, right, which is synthesized, and it's actually synthesized by this Sharingan tool. It looks like this complicated expression. So I don't want to go through this because I haven't really told you what the language is. But the stars are like regular expression, like stars. This sum is like some aggregate operator, and some base predicates here are like, checking something about the TCP field, something about the source IP address, and referring to the time since last packet and some numerical values. So that should give you a flavor of what the language looks like. As you can see that this whole expression is not super complex, right? I mean, it's kind of cryptic, but it's not complex. And so of course there is this catch here that a network operator, to interpret this, they will have to know this DSL, but the concepts are not, they are kind of things which typically people are used to, though the semantics is a bit idiosyncratic. But if they understand that, then they can edit this, right? So they could, for example, see that if the number of open sessions is greater than 4, that's the classifier that the tool generated based on the given examples. But if they understand what this is saying, they could change this threshold from 4 to 6, for example, if they wanted to be more conservative. So going to the exact synthesis question, so given a set of positive and negative packet traces, you want to find an expression which separates them. So each expression maps a trace to a value, so you want a separator. And the key challenges is that you have a rich set of constructs. The expressions involve numerical constants. So those who have worked on synthesis tools know this as a clear problem, that these handling these constants is a bit of a problem. The packet traces are long, which are thousands of packets. So even though the ideas from optimized search for Cygus solvers are very much relevant, we don't have an SMT theory for these quantitative regular expressions, and also for this NetQuery expression. So we had to really redesign the solver. And there are a number of the search techniques which are special. So there is something partial evaluation to do early pruning. And those are optimization techniques which go beyond what we already knew from building Cygus solvers. So I'm running out of time, so I'm going to skip through this particular optimization. But let me tell you a little bit about experimental evaluation. So there is this database of attacks called CICIDS 2017, and it has 8 types of attacks. In particular, includes this DDoS attack, and then slow law is another popular attack. So we get actually pretty high accuracy, which is comparable to the Skitsune. So you can't beat machine learning approaches in terms of accuracy. It's actually pretty good for both tools. But we actually synthesize these NetQuery programs, which can be interpreted. You can edit them. You can deploy these things very efficiently because we have this compiler and runtime systems for NetQuery time. And for 7 out of these 8 attacks, it took about 50 minutes. And for one of the attacks, it was about 300 minutes. So scalability still is something to be worked on. There are some things that we cannot handle, in particular mixed attacks. If the traffic contains a mixture of 2 different types of attacks, the tool kind of fails. So that's an opportunity for future work. So let me spend a few minutes to talk about research directions. So let me skip this. So this is just a summary of what I talked about. But in terms of infrastructure, if you look at publications in CAV, POP, or POPL, or PLDI, or more and more even in ICML and NeurIPS, there are lots and lots of publications on program synthesis. Many of them use Cygus benchmarks. Some of them use Cygus directly, and the other 2 infrastructures that I didn't talk about, but maybe the synthesis workshop has talks on, is like Sketch, by Solar Lezama and Rosette by Torlak. And some of these efforts do use it, but not all. And so this is actually kind of frustrating because, I mean, it basically says that, you know, there is, these infrastructures have to be better to be used more generically, right? Even then, this network traffic engineering example that I told you about, I mean, we couldn't use Cygus solver as is, right? Yeah. So one potential future direction is to keep this hook into SMT solvers, but not make it mandatory. So maybe, you know, the backend could refer to just a testing tool or an interpreter so that the search techniques can be used even when you don't have an SMT theory for the objects that you are synthesizing. And so that would, I think that's something people are talking about, but there is no infrastructure for that. In terms of applications, you know, I wanted to tell you about this great effort at Microsoft on building a PBE-based tools for automating repetitive code transformation. So they have a tool called Blue Pencil, and I just heard a talk about that last week, and it's just awesome. Like you have this program development environment where if a programmer makes some change, then you use as an example the old version and the new version that you did as an example, and you apply this as a code edit to the rest of the code, right? And so these examples are generated automatically based on what the programmer is doing, and the underlying technology is exactly the, you know, the PBE, the synthesis technology for PBE, and it's integrated in this great infrastructure, and that seems to be working very well. For super optimization kind of applications, I think there is this new effort on machine programming at Intel, and the motivation there is to porting code to heterogeneous platforms. The Skype-like efforts, and we are also now looking at how to synthesize data log programs. So going from data to logic, I think there is more potential there. And finally, in terms of solution techniques, you know, so this is, you know, making synthesis scalable is kind of, you know, it's an uphill battle, and we can't expect magic bullets, but there is a steady progress being made. But applying machine learning is obviously, you know, an interesting research direction. So one key challenge there is how do you represent code? And there's lots and lots of papers on that. If you're interested, here is an example paper. So learning graph transformations to detect and fix bugs in programs. So doing program synthesis, but using machine learning, using graph neural networks. It's a paper in iClear 2020, but it's just a one representative paper. So let me stop here and take questions in the remaining 5 minutes. Any thoughts?
Yeah, Anna, go ahead, please.
Yeah, hi. This is extremely interesting framework from TACS 2021. But first, I would like to ask a couple of questions about search, the enumerative search. Yeah. So when you talked about enumerative search, let's say if we have specification and then the specification changed only that slightly, do we have to do the whole search from the beginning, or can we somehow leverage what we already pruned or some kind of search that we already achieved?
Oh, great question. I think we don't know how to do that well. So in fact, you know, even in some cases, even as the set of inputs changes, we have to redo the whole thing. So it's, in fact, the specification hasn't changed, but in the CGIS loop, the set of interesting examples had changed. So you would think that you can reuse things from the past, but because of this pruning that we have done based on equivalence of expressions, which is tailored to the current set of interesting inputs, that gets reset. I mean, that equivalence gets destroyed. And so that's a challenge. It's, yeah, I mean, you know, I think there are opportunities there. it's hard to come up with tools that actually beat the current state of the art. Yeah.
Right.
But
Right. I see.
It's an interesting direction. Yeah.
I see. One more question, if I may, about the representation as a decision tree learning.
Yeah.
So this is also a very interesting approach. And you said that this kind of decision tree learning together with some probabilistic, I think, tools won the latest competition in 2019, and then nobody could beat it. So
sorry, just one clarification. No,
yeah.
that won the competition in 2017. Since then, CVC4 has incorporated not all of these, but some of these techniques. And now CVC4 has the SMT search, the verification tightly integrated with this enumerative search. And that actually beats everything. So that's the current winner, and it's at a stage where, in fact, it's a bit of a it's very hard to beat that. So that's why we are. So last year we did not have any tool which even attempted to beat it. Yeah.
I see. I see. But my question was, I guess, about the decision tree learning part. So what's the depth of the decision tree considered in this process? So how deep these decision trees can grow, and whether it would be interesting to look at the optimal size decision trees in terms of interpretability, of course.
Yeah. No, that's a great question. We haven't looked at that, but in terms of the ones that the current tools produce, I guess it would be. I don't know for sure, but I suspect it would be like 5 or 6. Yeah. So not deep enough to make the expressions complicated, but it's it's not like super deep also. Yeah.
I see. I see. Okay. My last question is about the last framework. As I said, super interesting framework. When you said that you cannot currently handle this mixed attacks, and this was my first question that I had, but you already answered that. But did you identify why the tool fails there? Can it not differentiate between two unknowns, or is there something that machine learning can do in between, for example?
So so actually this Kitsune also cannot handle mixed attacks. There may have been more recent work from the machine learning community that handles mixed attacks. Now, why does our tool fail? You have a good question, but I don't know the answer to that. I mean, this is very recent work, and yeah, it just it does. We know that it doesn't work. It fails miserably if there is a mixed attack. Yeah.
Okay, very interesting. I'll think about it. Thank you.
So, Sanjay, I see that you turn on your screen, so your video camera. So do you have a?
No, I didn't have a question. Just had a comment at the end. But thank you, Rajeev, for a really excellent tutorial.
Okay. Thanks.
Yeah. Are there any more questions? I mean, I have a question, Rajeev. Let's say we stay like 2 more minutes, 3 more minutes. So, did you guys also consider to use like continuous optimization tools, like nonlinear optimization tools? Because it looks to me you have a lot of discrete optimization tools plus some theories, associated with them. But
yeah, so so the question is how do you mix? How do you? So that's actually related to, can you use, say, for example, neural networks? Right? Yeah, so I could map the program, the expression into some vector, and then try to apply some machine learning technique, and then the gradient descender would form something, would correspond to some optimization, right? So there is this is an active area. So I guess one work which is kind of closest is this Swaraj Chaudhry's work, where he talks about neurosymbolic search. So you have so he combines basically the search in the neural networks with some discrete update in the program space. But it's definitely something to be explored more. Yeah.
I think I just want to make the comment, which is that next week we're planning to have a follow-up session where we'll have talks on algorithms for Cygus solving. So some of the people who've been very active in the recent Cygus competitions, we plan to invite them to talk about the underlying algorithms. So I hope this will be of interest to many of the attendees today. And also related to Rajeev's last answer, we'll also have another session on these machine learning inspired approaches to synthesis, maybe a couple of sessions later on. So all of this is coming.
Yeah, so I think with this, we are looking forward to see you next week. As mentioned, we are going to go deeper into what was presented today and what Ben presented. So we are looking forward to have you. Rajeev, thank you very much again for doing this. And I think with this, we can declare the session for today closed, and looking forward to see you again. Thank you very much.
Yeah, thank you all. And if you have any questions, or feel free to drop me a note.
Thank you.
Thank you, guys. Thanks.
Bye.
Bye.